So we've introduced Spirax-Sarco on a number of previous occasions, specifically the fact that we are a global organisation and we operate across a number of different business streams. We've got connectivity over Teams, but we don't have connectivity screen in the room. You could bear with us 1 second, please, Murat. I can see that the slides are moving on as far as Microsoft Teams is concerned, but the presentation in the room seems to have crashed.
Right.
Okay.
Yeah, so
We'll just spend a moment just introducing Spirax-Sarco whilst we get connectivity back in order here. Apologies for that. We operate across 3 different business streams. We've got our Steam Specialities division, we've got our Electric Thermal Solutions division, and we've also got our pumping division, Watson Marlow, that manufacture peristaltic pumps and also PTFE hoses that are commonly used in a number of food and beverage applications. As far as the UK and Ireland's concerned, we're a team that's about 200 strong, and we're made up from engineers that may be consultant specialists, product specialists, area engineers, commissioning engineers, and so forth. But we've also got a considerable range of configurators and calculators that I've spoke about in some detail before. Please do take a moment to look over all of those calculators and configurators on our website. I'm sure you'll find them in use. So whenever we talk about the use of steam, we need to remember that steam is used in a very, very wide and diverse range of applications. And it's true to say that almost every product that we encounter that's been processed or manufactured on a daily basis is likely to have encountered steam at some point in its process. But as far as today's presentation is concerned, we're going to focus on the uses of steam in the food and beverage industry. So what we're going to look at today, first of all, is we're going to have a very, very high level look at a number of traditional steam using processes in the food and beverage sector. And we're going to drill down and really understand the terminology we use whenever we're talking about steam condition, steam quality, steam purity. We're going to look at what the causes of a poor condition of steam are. And we're going to look at what that means to the process, the risks to the process. And then we're also going to look at how we can test the steam quality on a regular basis to ensure that the correct condition of steam is supplied to the process, whatever that may be. So as far as traditional uses of steam are concerned, well, there's a lot of very, very useful heat energy present within a mass of steam. Because steam gives up its heat energy isothermically, in other words, it doesn't cool down when it imparts its energy to the process, it means that it's got approximately 50 times more useful, more latent heat energy in a kilogram of steam when we compare that to a kilogram of, say, hot water. Because hot water needs to cool down by a certain number of degrees in order to heat the process. We also know that steam gives up its heat energy by condensing, by changing state from a gas back to a liquid again. So that means the speed of heat transfer, together with the fact that we've got considerably more energy in the steam, it means that steam is a fantastic source of energy for heating a process instantaneously. The example we can see on the screen is an instantaneous hot water heat exchanger. But on the secondary side, we could easily be using an alternative source of energy. It could be heating an alternative process. It doesn't need to be hot water. It could be concentrated juices. It could be dairy products, for example. And the fact that we can generate that process, we can heat that process instantaneously, means that we've greatly reduced the risk of Legionella, for example, on the secondary side in the case of heating hot water. But there are other benefits, such as the fact that if we're heating a process instantaneously, which we can using steam, we're going to have a much, much smaller footprint in the plant room. Other processes that can use steam that are commonly used in the food and beverage sector, jacketed vessels. As we can see, as long as we're providing the correct mass of steam at the appropriate pressure, remembering that steam's got a pressure-temperature relationship. So by controlling the pressure, we're manipulating the temperature. It means we can heat the process at the appropriate rate. We remember from previous presentations that I've delivered to the IMechE on steam fundamentals, we remember that we need to remove that condensate at the appropriate rate, so it's not going to back up and flood the heat exchanger. And we also need to vent the air away, remembering that air is a significant barrier to heat exchange. Other steam using processes, we've got retorts. Essentially a large scale sterilizer, if you will, or a large scale autoclave, typically utilizing a large area that can accommodate batch processes, maybe a couple of tons of beans or soups that are cooked in their own container. So of course we need to pressurize the retort. We bring it up to the appropriate pressure, we're controlling the temperature. So we need to put the appropriate mass of steam into the retort. And again, it's critically important to understand that we need to drain the condensate away and vent the air to bring it to the appropriate process conditions. CIP, another huge user of steam in the food and beverage sector. Whenever we need to perform clean in place for different processes to bring the water and the various rinsing agents up to the appropriate temperature. Pasteurization in the dairy sector. Again, we need to bring the product up to the appropriate temperature so that we can pasteurize the load on the secondary side. Again, meaning that steam is an excellent source of energy to allow us to do that. Vaporization, whenever we want to concentrate or evaporate water from a process, be it fruit juices or even in the dairy sector. Steam is an excellent source of providing that energy to provide that process requirement. Over towards the left-hand side of the screen, you can see a single-phase evaporator, whereas over to the right-hand side of the screen, you can see a two-phase evaporator. It could easily be a three-phase or maybe even a four-phase evaporization process. And the thing to bear in mind is the more stages of evaporization we have, the more efficient the process becomes from an energy perspective, for the simple reason that we can use the energy that's present in the vapor to then provide the energy for the next phase. So the processes that we've spoke of up to this point have been what we would refer to as indirect processes. And that's because the steam doesn't actually come into contact with the food product or the atmosphere. It's by no means an exhaustive list. They are just some of the typical indirect steam using processes. But we can also use the steam directly. In other words, that's when the steam does come into contact with the product or the atmosphere. So the example that we can see on the screen at the moment is whenever we're using steam for humidification purposes. And typical uses of steam humidification in the food and beverage sector are proving bread or pizza dough, for example. But we can also use humidification for curing cheeses, ripening avocados, bananas, tomatoes, for example. So the uses of steam in applications such as this mean that the steam is going to come into contact with the product. It's a direct usage of steam. And of course, if the steam is being absorbed directly by the product or the atmosphere, it means that we don't have any condensate to recover. The steam and the condensate, and whatever the steam is carrying, could potentially contaminate that product. Other direct uses of steam, sterilization. Now, when we think of sterilization, that could be for cleaning purposes, for sterilizing a pouch or a container, or it could be for squirting a small mass of steam across an open jar, baby food jar, for example. And as that steam condenses, its volume collapses, and of course, that's partly responsible for pulling down that compressed dimple that you see as a security feature on the top of baby food jars. Again, it means that whatever the steam is carrying can become part of that product or atmosphere. And a relatively new means of using steam is what we refer to as steam infusion. If you think back to that jacketed vessel that we spoke about, steam gives up its heat energy across a thermal barrier to heat a product or a process slowly. The steam doesn't actually come into contact with a product. Now, if we had a steam lance that fed into the jacketed vessel, say from above, then it would spray a controlled mass of steam directly into the product or process. And the benefits of doing so in a controlled fashion are, first of all, the steam would cook the product, it would bring it up to the appropriate temperature, it would hydrate the product. The moisture that was present in the steam would become part of the process, and it would macerate the product as well. So if we had soups or sauces, we'd be able to bring the product up to a controlled consistency fairly easily. Now, from an energy perspective, it's also beneficial because if we're adding the steam from the inside of the product, it's going to cook from the inside out, which means we're reducing the burden of CIP, we're increasing the cooking time of the process, and if we're reducing the risk of product burn-on, we're getting an improved product consistency. Now, on the downside, it does mean that we may perhaps need to speak with the food scientists just to make sure that they've protected the recipe, to understand the intricate differences between cooking a product in a jacketed vessel indirectly and comparing the differences that would be brought to the process by cooking it through steam infusion. So now we understand that steam can be used in a wide range of applications in the food and beverage sector. We understand that steam can be used indirectly, where there isn't a risk of contamination to the product or the atmosphere. We need to understand that if we are using the steam directly, then that risk is present. So the first question that we need to understand whenever we're talking to our steam using client is, what are you using the steam for? What's the purpose of the steam? Once we know that, once we know the question, once we know the answer to that question, we need to consider the quality of steam that our client has on site. Now, if we're talking to a utilities engineer or a maintenance engineer, if we're talking to them about a steam quality, especially when that steam isn't going to come into contact with the product, typically we mean reasonably dry, reasonably clean, where we're not at risk of any mechanical issues such as erosion, corrosion, water hammer, or even any build-up of scale on the surface of the heat exchanger. But whenever we're using the steam directly, it's critically important that we know exactly the condition or the quality of steam that we're working with. And the terminology is such that we would split that into two different areas. First of all, we've got what we call the thermodynamic properties. That's the physical properties of the steam. In other words, how dry the steam is. In other words, how much air and other non-condensable gases are present within the steam. And then finally, how much superheat is present within the steam. And then we talk about the purity of the steam. And the purity of the steam specifically references whatever the steam might carry. I mean, the steam is a fantastic vehicle for heat energy, but it can also carry other things with it. For example, an excess of water vapor or carryover from the boiler. That can result in corrosion, especially when we're conveying the steam hundreds or thousands of meters in steel pipework. The better the steam, the more likely we're going to get rust and iron oxide present within the steam. Boiler scale. If we get an excess of foaming in the boiler, that's going to dry out as a scale, and that scale is going to be carried by the steam to the process. But we can also have boiler chemicals that are carried along with the moisture into the pipework, and that's going to be carried by the steam towards the process. So we need to think about the steam in those two different areas. We need to think about it in terms of the thermodynamic properties and also the purity. So how do we measure the quality or the condition of the steam? Well, one of the best ways of measuring that in the food and beverage sector is by referencing BS-EN 285. That helps us to put value on whatever we're working with, the condition of the steam. And it states that we want the steam to be 95% dry. Up until relatively recently, that used to be 90% dry. It's now changed to 95%. Why do we want it to be 95% dry? Well, if we know how dry the steam is, we know how much energy is present within the stage. Many engineers will reference steam tables to understand the energy content of the steam, but that only applies when the steam is 100% dry. When we've got dry saturated steam, the wetter the steam, the further away from those values that are detailed in the steam tables that steam becomes. We want the steam to be 3.5% by a condensed sample of that steam, 3.5% air and other non-condensable gases. Why? Well, the air and the non-condensable gases are a huge barrier to heat exchange. So it means that we can no longer rely with 100% certainty or accuracy on that pressure-temperature relationship. There's going to be less energy present within the steam. And we want to ensure that there's less than 25 degrees of superheat present within the steam. Now, fortunately, in the food and beverage sector, superheat is relatively difficult to come by. A small amount of superheat can have a beneficial effect, especially if we've got very wet steam, because it can have an effect upon drying that wet steam. But if we've got too much superheat present within the steam, it's not a good thing at all, especially when we're using that steam for heat transfer applications. And that's because there's actually more useful heat energy present within steam at a lower pressure and a lower temperature than there is at a higher pressure and temperature. So it means that the steam is now incapable of imparting energy to the process under the design conditions. So BSEN 285 helps us to benchmark those thermodynamic properties concerning steam quality. Now that's important regardless of whether we're using the steam directly or indirectly. But then we've got the purity of the steam as well. And that's quite a difficult one for us to benchmark. That's whatever the steam carries, what's contained within the steam. And as we've mentioned, that could be an excess of moisture. You know, that steam can exist when it's far, far less than 95% dry. The boiler will operate under different conditions, and that's why it's critically important that we've got periodic testing, supervision, water treatment, and that we've also got the most sophisticated controls that we can have in the boiler house to ensure that we can get the best possible condition of steam being produced as it leaves the boiler house. And of course, if we've got very, very dry steam, we're more likely to get far less corrosion. We're going to get less rust and iron oxide present in the pipe. Highly unlikely that we can guarantee that we've always got dry steam. So we need to contend with the fact that we're likely to be exposed to a little bit of risk there. Boiler scale. The high concentration of boiler chemicals that are going to be drawn out of the boiler in the form of foam. And then, of course, those boiler chemicals that can be drawn out whenever the boiler primes and that steam gets excessively wet. So the steam is a vehicle for potentially all of those causes of contamination. Now, the biggest or the most important raw ingredient of steam is, of course, the water quality that we use. And you can see up on the map on the screen at the moment, we've got a map of England. And as far as where we're based right now in Warrington, you can see that we're very, very close to the T-junction of three different water qualities. So we could have a client that's got an identical process in three different parts of the UK, but they're actually consuming different water qualities. And we then need to complicate things further because our client may not necessarily be using water from the mains. They could be using borehole water, they could be using reclaimed water from the process, river water, rainwater, and each of those water qualities is going to have a different chemical and mineral balance. And of course, they're going to need to employ an experienced water treatment professional in order that we can make sure that that condition of the water is suitable for the boiler and for the process. Here where we are in this part of the world right now, we could be bringing water from different reservoirs in different parts of the county at very, very short notice. So it's critically important that we ensure that the water treatment regime accurately matches the condition of the water that's supplied, and that the water treatment pumps are routinely calibrated. Whatever is present within that water and the chemicals that we condition that water with are going to become part of the process, especially if we're using that steam for direct application. So some of the water treatment chemicals that our clients may be using, that they're shown on the screen, and they can be used for a wide variety of purposes. Principally, it's to protect the boiler, protect the pipework, and to ensure that the steam is of a sufficient quality that it's not going to create any problems with the wider infrastructure. Now, that's fine whenever we're using the steam for indirect purposes, where it's not going to come into contact with a product or an atmosphere. But what about when we're using the steam for direct injection, like the humidification purposes or sterilizers, for example? Well, I can't even pronounce half of the chemicals on the list towards the left-hand side, and I'm not going to try to, but I'm pretty sure I wouldn't want those becoming part of the process. Now, quite often our steam-using clients, they would say, well, the boiler chemicals that I'm using, they're FDA approved. That means they're safe for the process. And that's not necessarily the case, because the FDA approval or the food safe approval chemicals, that only actually applies when those chemicals are in vapor form and when they're supplied at the expected or appropriate concentrations. And of course, when we've got the boiler cycling under different conditions, we appreciate that we can't guarantee what those concentration of chemicals are. And when we get foaming that exists as a result of a high concentration of chemicals, that foam means that those chemicals are now no longer a vapor, and it means that foam is likely to dry out as a scale. And that scale can cause erosion as it passes around the network, especially if we're conveying that steam at 40 meters per second or thereabouts, which is relatively close to 17 miles an hour. It can cause erosion of sensitive components, making it very difficult to control process conditions. But it also means that that scale can contaminate an atmosphere. So when you think about sodium hexa, I'm not going to try and pronounce it, when you think about that potentially becoming part of the process or atmosphere, it's important that our client appreciates that, because that is when steam is becoming an ingredient. So what we can see at the moment is it's just a moving image, it's just a video image of the surge in boiler pressure. And a boiler can surge in pressure or fall in pressure during different operational cycles. Whenever there's a huge demand for steam by the process, the boiler pressure will drop, the steam bubbles will expand, and it will agitate the foaming layer. That foaming layer will become deeper and deeper, and that's when that foam can become drawn out of the boiler, along with the steam, into the pipework, and that's when the steam carries that foam. That foam is really going to contribute to that wet steam that we've spoken about. Wet steam, it means we're more likely to be exposed to the risk of erosion, corrosion, and of course water hammer. As that foam dries out and produces scales, that's when we're at risk of...
1 minute, sorry, I think we're duplicating. Sorry. Sorry, carry on then.
That's when that foam dries out with scale. We've got a very, very high concentration of boiler chemicals that could potentially become part of the process. So what we can see on the screen at the moment, it's actually a photograph of a couple of bottles of condensed steam, or condensate, if you like. And this really does demonstrate how steam is a carrier, or steam is a vehicle, not only for that energy, but for also whatever else may be present within the boiler chemicals, and rust, scale, and other particulate. So if we're using that steam for proving bread, if we're using it for curing or drying pasta, or humidifying cheeses, or even sterilizing baby food jars, you can appreciate the risk of contamination that is posed by these two photographs here. So just a few direct steam using processes in the food and beverage sector are shown up on the screen. Again, it's by no means an exhaustive list, but there is quite a range of very, very popular processes that will come into direct contact with steam and whatever it's carrying. And the thing that we need to bear in mind is the risk that that poses to the product. So in certain cases, it may well be that those contaminants are affecting the pH of the product. And if the pH of the product is affected, then the shelf life of the product could become affected. And that's when the food scientists will certainly want to be aware of that. Or it could well be that whatever it is that the process is carrying could affect the quality of the process. You know, there could be an allergen, or there could be a risk to the patient, to the consumer's health there, if that were to be consumed and if there were to be an adverse reaction. So whenever we're talking about food contact materials, quality managers that are employed by the food and beverage steam using client would typically be very well aware of standards such as EC 1935-2004 that states that any product or material that comes into contact with the food needs to be appropriately regulated or manufactured out of a food safe hygiene material. Well, if you think about it, steam comes into contact with the product and the atmosphere as well. So it's important that we ensure that the way that we're generating the steam and distributing the steam so it arrives at the process adhering to the standards that are defined by EC 1935-2004. Steam is by nature going to be a food contact material in itself. So just taking that one step further, we could have a product, doesn't really matter what it is, but quite often our client is going to have a product that uses steam. And if we're using the steam for direct injection purposes, let's say that steam infusion process that we spoke about previously. Well, it could well be that the process is 60% raw product, such as tomatoes. Fill it up with 20% potable water, and the remaining 20% is made up of the water that's present within the steam. That is the process. But if you look at the ingredient label and that kind of soup, it would likely say 60% tomatoes and 40% water, because after all, when steam gives up its heat energy and condenses, it's water anyway. The problem is that ingredient label hasn't taken into account whatever the steam is actually carrying. I'm pretty certain I've yet to see a can of soup, can of beans, or whatever that lists rust, sodium, whatever that unpronounceable chemical was, rust, scale, and even if we've got an excess of water, or even if we've got air and other non-condensable gases going into that product, then the consistency of the product, the acidity, the alkalinity, the amount of heat going into the product, it's not going to be what the process was expected. So whenever we're using steam directly, it's important that we remember that the condition of the steam or the condition of the water is going to be exactly the same as the potable water that is being used in the client's process. They will be all over the water chemistry whenever water is being used directly in the process. They'll be using an excellent condition of water, perhaps even far better than potable water is. And it's important that we apply the same care and attention to the steam itself. But of course, we appreciate that we've got to put a lot of chemicals into the water whenever we're using it in the boiler house for purposes of protecting the boiler structure. Now, where does that risk of contamination come from? Well, depending upon the water source that we're using, it could be Towns water, it could be reclaimed water, it could be borehole water. It's going to have different chemicals, minerals, and other particulates present within it. We need to have the appropriate water treatment regime. We'll be treating that with a new cocktail of different chemicals. So, of course, whenever the boiler pressure falls, that foaming layer is going to expand and it's at risk of being drawn out into the infrastructure. We know that we can get pipe scale in the infrastructure. Typically, we're going to be moving that steam hundreds, maybe even thousands of meters in carbon steel pipework. So we expect that, especially if we get wet steam, we're going to get some corrosion. And typically, our client is going to be using steam for multiple processes. Some could be direct, some could be indirect. So it may well be that one of those indirect processes is pinhole. So we may have product passing across the thermal barrier, back into the condensate recovery line. If that condensate goes back to the boiler house, into the hot well, and into the boiler, then that product could potentially cross-contaminate the direct steam using process. There are multiple pathways of contamination into a plant steam system. We've got to be aware of that. We've got to be aware of what the risk is. So what we can see up on the screen at the moment is what we call the steam condition triangle. That helps us to understand the different qualities or different conditions of steam that exist. Right at the bottom of the triangle, you can see plant steam or grey steam, utility steam. It's got a lot of different names. It's basically the steam that we're all familiar with, that's produced in a huge steam boiler and then distributed hundreds, thousands of meters around site in carbon steel pipework. What's wrong with plant steam? Absolutely nothing. Really depends what we're using it for. If we're using that plant steam for indirect processes, a little bit of particulate, a little bit of scale, steam that's slightly wet from time to time, it's not going to be a huge problem. It might not work as efficiently as we like, but there isn't a risk. But whenever we're using that steam for direct application purposes, we need to apply a hazard. Now, the vast majority of our steam using clients, they'll already be applying a hazard on their sites. If we ask to visit the process, the production line, the first thing they'll ask us to do is to put the foot coverings on, put a hairnet on, wear a white coat, perhaps even wear gloves and a face mask. If you were to ask the production manager or the quality manager why, they would look at you like you'd fallen off another planet. They would say, well, we can't live with the risk that you could contaminate our process. If you were to ask them statistically what that risk was, they'd say, well, it's minute. It's very, very little risk, but we don't have an appetite for risk. But there's a far, far greater risk that the steam is going to contaminate the product and the process than you are. So it's appropriate that we apply a similar hazard. And the way we do that is by moving up the steam quality triangle. So above plant steam, you can see that we can improve the steam quality or steam condition by applying what we refer to as filtered steam. And it's important that we use the correct terminology here, because some clients will use the terminology clean steam when it actually isn't. It's filtered steam. And the difference between filtered steam and clean steam will hopefully become apparent in the next few slides. So filtered steam, a steam filter, it's a mechanical filter. Now, if we've got a 5 micron element, which is very commonly used whenever we're using filtered steam in food and beverage applications, it's important to remember that a 5 micron element, it will only remove 95% particulate 2 microns and above. So anything that's less than 2 microns is going to go straight across the filter. And that can include quite a lot of potential contaminants. And it will only remove particulate. So it won't remove moisture, it won't remove air and other non-condensable gases, and it won't remove any chemicals that are in vapor form. The other thing to bear in mind here is that filter will also have a coalescing effect. So especially if the steam is slightly wet, that moisture is going to coalesce, and it means that we need to remember to install the appropriate steam trap. And we also want to vent any air away at that point. If we don't do that, we're at risk that the filter can either airlock or it can flood with condensate, at which point we're not getting steam to the process. Now, what you need to appreciate is that what will quite often happen in our experience is the maintenance team or the production team will get around that very, very easily by just removing the elements. So if we remove the element, we've got a steam filter, but we no longer have filtered steam. It's also important that that steam filter is being sized in accordance with the pressure drop across. So never size line size, because the pressure drop caused by that filter means that we may no longer be getting the required mass of steam across the filter at the expected pressure. Again, when that happens, the production team will typically overcome that by removing the filter. Not necessarily aware of what the risks to the process are. The other thing to bear in mind is if we're installing a filter and an element, it needs to be 316 stainless steel, so it's not at risk of corrosion. And therefore, if we've installed a 316 stainless steel filter, everything that's installed downstream of the filter, the pipework that connects the filter to the process, that also needs to be in 316 stainless steel. If it isn't, we're just reintroducing that risk of corrosion. So hopefully you can appreciate that filtered steam, it reduces the risk of contamination to the process, doesn't eliminate it. So the only way that we can eliminate the risk of contamination to the process is by going back to that HACCP. And you can see that there's a red line that separates filtered steam and clean steam. And that's when we then move up the triangle and we then generate the steam of the process from a steam to steam generator. And that's probably best explained on the slide that we can see now. So if we're using an excellent condition of water, many of our steam using clients in the food and beverage sector, they'll already have a supply of potable water or better, maybe even RO water, demineralized water, whatever. If it's an excellent condition of water, very, very low chemical ppm, and therefore it means that we no longer need to add further minerals and chemicals to it. So if we feed the first tank that we call the preheater or the degasser, and the second tank that sits below it, that's the main steam generator, with that excellent condition of water, we can use the plant steam. And if we're feeding that plant steam through a 316 stainless steel coil, we're using the steam indirectly. So there's no risk of chemical contamination. So that excellent condition of water. The first degassing tank, we want to bring the temperature of the water up to a very high point for the purpose of driving off the oxygen and the non-condensable gases. That hot water is then fed down into the second pass, the steam generator, at which point we're bringing that high temperature hot water up to the point where it evaporates and produces steam. If we've got chemical-free water, we get chemical-free steam. Be degassed. And if we can then distribute that chemical-free steam in a very, very short run of pipework to each individual steam using process, 316 stainless steel, then of course we greatly reduce the risk of that steam further degrading, getting wetter and wetter. And we can also ensure that we've eliminated the risk of corrosion or contamination to the process. So a clean steam generator, such as the one you can see over towards the right-hand side of the screen, that would typically be used for relatively low loads for individual decentralized processes. Typically, it would sit very, very close to a steam using process, piece of capital equipment. For larger clean steam using processes, it may well be that we're using centralized clean steam generators, such as the one you can see over at the left-hand side of the screen. It really depends upon how much clean or chemical-free steam our client is using and what the individual applications are. The thing to bear in mind is we could actually use potable water, tap water, to produce that chemical-free steam. We get steam that we've produced without there being a significant risk to health, because if we then condense the steam again, it would be the same as the condition of the water that was being used to supply the steam generator. But in reality, we want to protect the elements in the generator from the risk of scaling in exactly the same way that you would do with your kettle at home. Now, we're all familiar with the purposes of steam trapping on the plant steam infrastructure. We've gone through that in previous webinars. In short, the purpose is to drain the condensate away and protect the infrastructure to keep the steam as dry as we can. But it becomes more critical whenever we're talking about protecting the steam downstream of the clean steam generator and ahead of the process. Well, remember, we need to guarantee that that steam is 95% dry or better, and we need to guarantee that we've got absolutely zero risk of that condensate backing up and resulting in a pathway or resulting in an opportunity for microbial growth to present itself. So there are a number of different steam traps that we could use on a typical plant steam system. But whenever we're using clean or chemical-free steam, we want to consider a thermostatic steam trap. The reason is when we use a thermostatic steam trap with an element that is classed as near to steam or an element that will open typically within plus or minus 2 degree temperature fall in the condensate, it means that we can guarantee that we've eliminated the risk of any condensate backing up and flooding the infrastructure. And it means that in the very unlikely event that that steam trap were to fail, it'll do so in the open position. Now, in previous presentations, we've mentioned how when steam traps fail in the open position, it can result in the loss of energy, because that steam will be lost to atmosphere. When we're talking about protecting the process, we need to remember that typically we're talking about a relatively small mass of steam in the great scheme of things, but it means that the main objective is to ensure that the process is protected against that risk. You'll also see down towards the bottom right-hand corner of the screen how a clean steam trapping station is different to a trapping station that we'd expect to see on a plant steam system, where we've got the dirt pocket. And of course, the purpose of the dirt pocket is to allow all of that heavy particulate, that rust and scale, to settle out, so it's protected the steam trap against blockage or erosion against that heavy particulate. But if we're generating clean steam, where we don't have that particulate being present, then the purpose of the dirt pocket is redundant. And it also means we want to ensure that the condensate passes straight across the trap so that we haven't got any condensate trapped, which, as we know, could result in an increased risk of microbial growth. So, of course, if we've gone to all this effort to produce an excellent condition of steam that complies with that EN 285 standard, then we need to be able to prove that we've got the condition of steam that we require. So it's critically important that our client has a periodic steam quality test. Now, it's really down to the client to determine how often they need those tests. Many clients will have them weekly, monthly, or maybe even once a year. It's important that they understand that if they've gone to all of this effort to provide an excellent condition of steam, they need to be able to prove that that is the condition of steam that they are providing. So the first steam quality test that we have is the dryness. We want the steam to be 95% dry or better. And we can test the dryness by, we connect a flask containing a known mass of water at a known temperature. We connect it to two different test nipples on the elbow that you can see on the screen in the picture towards the far right. When we've run the steam system for a certain period of time, we can then disconnect the rubber tube from the test nipples. We re-weight the flask, take the temperature. Once we know the mass change and the temperature change, we're able to determine the overall dryness that the steam exists at. The second test is for air and non-condensable gases. Again, we connect the rubber tube to different test nipples that exist on the elbow. When we're condensing the steam in a flask of cool water, then that steam will become absorbed into the product, and of course the mass will increase. The steam will then displace the water from the beaker into a measuring barrette that you can see at the bottom of the screen, and we'll find the air and the non-condensable gases rise up through an upturned funnel. And once we've measured 100 ml condensate, once we've displaced the water in the flask by 100 ml, we can then identify how much air and non-condensable gases are present in the upturned measuring cylinder up towards the top right-hand side of the screen. Remember, we're aiming for 3.5% by volume or less in order to apply to those EN285 standards. And then we test for the superheat. And testing for the superheat, we want to test the temperature of the steam once it's fallen to atmospheric conditions, 0 bar gauge, and also we reference that with the condition of the steam that exists at the pressure that is determined within the pipework. So once we know the temperature difference there, we can determine how much superheat is present within the steam. Again, we're aiming for 25 degrees or less. So those steam quality tests, they do need to be taken periodically if the client is taking their steam quality seriously. When it comes to the purity, that's a little bit more difficult to define. But what is important is that we've got a number of different test points located around the infrastructure. Now, the most important place for us to test the quality or the condition of steam, right next to the point of use. Pointless as saying we've got an excellent condition of steam 1,000 meters away, because it could degrade by the time it gets to the point of use. We need to measure the quality or the condition of the steam next to the point of use. But it's also good practice to test the condition of the steam periodically, monthly, quarterly, in the header and the distribution pipeline. It helps us to have peace of mind that we're not following poor working practice. It gives us a really good indication as to whether we're generating a good condition of steam in the plant steam boiler. For example, if we've got a very, very poor condition of steam in the plant steam boiler, there might not be enough energy in the steam to bring the clean steam up to the appropriate design condition. So the starting point is really ensuring that if our client is taking steam quality seriously, even if they've got a plant steam system, or especially if they've got a clean steam system when they're looking to move towards the EN285 standard, it's critically important that they're in a position where they can prove the steam quality that they have on site. And the only way we can do that is by having the appropriate test points, an example of which is being shown on screen at the moment, because that means that we can undertake those 3 tests: the steam quality, the air and non-condensable gases, and also the dryness. Without those test points, we can't prove the condition or the quality of steam. Now, when it comes to the purity, typically that is something that the client will want to take responsibility for themselves. As we've mentioned, the purity of the steam is what the steam carries, and that can change over a very, very short space of time. The way that a client would typically test for purity, well, they put that steam across a sample cooler. It safely take the steam from being a high pressure hot gas to a single phase condensate at a low safe pressure and temperature. And they can then take a sample of that condensate away to the labs. The microbiologists would run some analysis to find out exactly what the steam contained. But there are a number of different types of sample coolers. We could have a standard sample cooler that we used on a plant steam system or in a chemical-free system, and it's appropriate that our client have the appropriate sample cooler to ensure that it wasn't the sample cooler itself that was imparting the impurities to the condensed sample. So there's a lot to go through there, and I really do appreciate you taking the time to attend and dial into the presentation today, and apologies for those technical issues we had early on. These hiccups do happen when we're new to these hybrid systems, but just to summarise what we've gone through today, we need to consider that steam can impart risk to the process. We need to remember that if we've got a risk to the process, not only can it affect the product quality, and that could result in product recall, or it could result in, worst case, an adverse allergic reaction. We need to remember in the food and beverage sector, I think we're all aware of Natasha's law that states that we've got to accurately label every ingredient of a product. I've never seen any of those unpronounceable boil chemicals present on a sandwich wrapper or on a tin of soup. We need to remember that that can result in a huge health and safety risk, or it can result in legal action and damage to our client's brand. So we need to remember that whenever we're using the language steam quality, we need to be really certain that our client understands the terminology we're using. We need to say, what are you using the steam for? Are you using it directly or indirectly? If you're using it indirectly, you can have a resulting slowdown of the process time. But if you're using the steam indirectly, sorry, if you're using the steam directly, that steam will be an ingredient of your product. Now, BS EN 285 states that the steam should be used, or the steam needs to be provided at measured qualities. Dryness, superheat, air and uncondensable gases. It doesn't state that you must use clean steam, but the only way that we can guarantee that those EN 285 standards are achieved is by using clean or chemical-free steam generation. So I'd like to thank you very much for your time once again, much appreciated. If there are any questions on what we've gone through today, then I think we'll throw open to Murat over Teams at the moment. Beg your pardon, sorry, Pamela's got the control of the questions in Teams. So we'll have a look first of all at any questions that may have been asked over chat, and then we'll address those, and then we'll throw open to the guys in the room.
So just do it the other way around when I get to grips with the question.
Let's do it the other way around.
Any questions in the
Any questions in the room?
There are some questions in the chat.
No problem.
Sorry, yeah, the technical issues we had here, just to explain, is that the screen, the massive, huge screen was not displaying the presentation, so we've had to look from laptops. Hence, I shared my laptop with the people here, and Dan used his. Those were our technical issues. So I hope it didn't spoil the viewing at home.
The screen went to sleep.
Yes.
I can pass on the questions if that's.
Sludge conditioning. What we want to do is we want to encourage the minerals that may be present within the water to solidify and to fall out towards the bottom of the boiler, similar to the chemicals and minerals you find in your kettle at home. Yeah. And that's when we perform what we call bottom blowdown. So we would open a valve at the bottom of the boiler, we'd blow all of that nasty sludge away to waste. We can't recover it or reuse it anywhere else in the process. But it's important to remember that some of the chemicals and minerals will fall out into the bottom of the boiler as a heavier particulate, and others will be held in suspension. So we use those sludge conditioners to encourage as much of the chemicals and minerals to solidify, and so that we can take it away as a heavier particulate. Thanks.
Are there any other questions here?
On our approver systems, I've never seen anybody put test ports on our steam trains, and I've just taken that away. I missed the detail on the slide. Was that a 1/4 inch BSP was the minimum, or would you recommend something bigger for test ports?
1/4 inch BSP. Yeah. I can make a PDF of this available for you, and we've got a guidance note as well that can ensure that either yourself or your client is designing that test elbow to the appropriate standards.
So, and again, in the bakery industry, again, humidification is direct. we tend to get steam supplied to us at between 5 and 7 bar in these places. Is there likely to be any superheat in that?
Very, very, I would say nigh on impossible. Nigh on impossible. Superheat generally occurs when you're falling from a high pressure to a very low pressure in a very short space of time.
Yeah.
And
These are relatively low pressures.
in many applications, a little bit of superheat can have a beneficial effect because it's going to dry any steam that exists at wet condition. But we need to guarantee that the process isn't at risk. What we need to remember is that when we talk about steam quality or steam condition, it can change in a very, very short space of time. So it's like comparing a photograph to a video. When you get a photograph, you can say at 10 o'clock on a Tuesday morning, my steam was in accordance with EN 285 standards. But on the Wednesday afternoon, it could be all over the place. It can be your steam's 80% dry, you've got 10 degrees of superheat, and you've got 5% air and non-condensable gases. But you tick the box to say that your steam quality standards were as expected in accordance with the EN 285. So if we've got very, very frequent testing, then of course that helps. And that's really where the ease of testing with the appropriate test points and test elbows really does help our client.
Sorry for you. Yeah. A question from Keith online. In steam infusion, how do you calculate the residual amount of condensation steam is added to the batch recipe?
Residual condensate. I'm assuming that what Keith means there, correct me if I'm wrong, but I'm assuming what it means is how do we know how much water is going to become part of the process? And the short answer is unless we're producing steam at EN 285 standards, we don't. Because 1 kilogram of steam, it should condense to produce 1 kilogram of condensate or 1 kilogram of water. But of course, if the steam is being provided at unknown pressures, masses, dryness values, then it can really impact upon the process because we just really can't guarantee with any real accuracy what's going into the process, which makes that EN 285 standard all the more important to us.
Next question, same person. Are there significant cost implications in providing the higher grade of steam quality?
Yes.
Yeah. Ballpark or?
As a very, very broad rule of thumb, you need to be multiplying by a factor of 3. You need 3, maybe even 4. You've got to bear in mind we're looking at food contact materials, 316 stainless steel or better. We're looking at excellent water treatment. It all comes down to our client's appetite for risk. If you talk to one of the major blue chip manufacturers, they don't have an appetite for risk. It's as simple as that.
Can you give an example of clean steam in food and beverage and filtered steam in food and beverage and the reason for the difference?
The reason for the difference, that's an easy one, cost. That's the reason for the difference. Filtered steam, it's a mechanical filter, it's a component that you can maintain on site. The risks are, as we've mentioned, you're reducing risk, you're not eliminating risk. And that's not to say that there's anything wrong with filtered steam. It depends upon what the client's appetite for risk is. And if the client is happy that the risk is minimal or that the risk is acceptable, then filtered steam, nothing wrong with it, providing that steam filter has been sized, selected and installed correctly, and most importantly, that it is maintained correctly. Typical applications, well, filtered steam, or quite often referred to as culinary steam, please don't ever refer to it as clean steam because it's not. It's filtered or culinary steam. That's commonly used in, you can use the example of bread proving, it could be used in the dairy industry. Clean steam, we're moving towards a high-end process. If we're talking about baby food, whether it's going into those organic pouches, if we think about a client that's manufacturing a kosher product, or manufacturing a halal product or a guaranteed organic product. Well, all of the boiler chemicals that are present within the steam, they're not going to tick a box for all of those sectors. So it could well be that that steam using client is likely to be audited at some point in the future. And it could well be that any number of retail partners are just going to draw a line under that product if they're ever audited. But it certainly wouldn't be a good PR exercise if you found out that any of those unpronounceable chemicals that I can't even recall were entering into that organic, halal or kosher product.
How do you measure cleanliness of the steam within the process?
Short answer is we don't. What would typically happen is we would provide a mechanism, that sample cooler, for the client to test that themselves.
Yeah.
9 times out of 10, they would do that in-house because they're testing the quality of their products on a regular basis. So they'll have the technical know-how, the microbiologists, in order to do that in-house. If they didn't, then we'd recommend that they went to a specialist, third party, in order to do that. But they need to appreciate that steam is the vehicle for those particulates and those impurities that we spoke about.
With water shortages and droughts, does this affect the clean steam process?
Water shortages and drought? Not really, because it's if as long as we're being responsible with regards to the amount of energy that we're using from the plant steam boiler. Typically, we're generating much greater masses of steam, and therefore the opportunity for water loss is far greater on the plant steam side than it is on the clean steam side. But it's responsible to ensure that we're minimising the blowdown from that sludge condition we're talking about. It's responsible for us to keep that at a minimal level. That's typically dictated by the boiler manufacturers. But we do know that in certain parts of the world, water is, in many cases, a more important commodity than fuel is, which is the case certainly in Western Europe.
Appreciate we're 7 minutes over. Do you want to go through the last few questions, or do you want to?
I'm more than happy to, as long as I'm not keeping you guys.
Just 3 more questions, unless there's any more going to appear. Are there any machine learning or AI solutions to predict purity?
Purity, no. Thermodynamic properties, theoretically, yes. We did have a solution that was at the R&D phase a couple of years ago. We didn't move ahead with commercialising it, and I believe that was down to if we were able to help the client demonstrate that their steam process was not within the N285 standards 90% of the time, then production wouldn't be moving forwards. So we're trying to move towards a position where we can help our client not only demonstrate that they've got the applicable steam condition, but they can take the appropriate remedial action at the same time. So connectivity is moving at pace very, very quickly. And my colleagues in our connectivity team will be able to address those issues in the very, very near future.
How could the consumer be informed about whether the manufacturers are using high quality pure steam or just filtered?
How could the consumer be informed? Well, it's a fine line, because our responsibility is to educate. It's not to scare anybody. It's just to educate, and it's really down to the steam using side to accept the risk. They know their processes better than anybody. It's just down to the fact that they may have considered steam as a utility, like electricity or gas, and that's not the case, because the quality can differ for reasons we've gone through. Now, a lot of retailer groups, your major supermarkets, they're becoming more and more educated. And quite often they're spot auditing a lot of manufacturers and saying, show us your clean steam. and the manufacturer is saying, well, here it is. And, you know, Mr. Supermarket is saying, well, that's not clean steam, that's actually filtered steam. And that's not in accordance with the contract that we've agreed. And of course, it then becomes quite costly to stop production and make the appropriate infrastructure changes. So quite often the drivers are coming from the larger retailers because they recognise that they need to protect themselves from being exposed to Natasha's law. If a major supermarket is not listing the ingredients on their sandwiches or on their tin of soup appropriately, then they're the ones that are going to suffer the brand damage. So all we're doing is passing the responsibility down the line.
Yes, yeah. Are you able to come to site to visit systems at cost to measure steam quality or for both direct and indirect use of steam in the food processes? Do you provide consultancy support?
Yes, it's the bottom line there. Typically, it starts with your plant steam system. It works backwards from there. So steam track audits, steam quality audits, clean steam audits, condensate sampling, any process that helps the client to understand, first of all, what their existing situation is, standards that they're working towards, and we can put a roadmap in place to help them get there. And all they need to do is either contact myself directly or their local Spirax Sarco representative, wherever in the world they may be, who can make that happen to support.
That draws an end to the questions. So thank you very much, Dan, for coming this evening and giving us an interesting talk on steam and its use in the food and beverage industry. I certainly learned a lot over the evening. The uses of steam, why it's important for its purity, its quality, and maintaining that quality, satisfy the standards. I'm from the water industry, so I understand the water quality aspects of that side of the talk. And if everyone who wants a CPD certificate can they email Murat on the contact details above. If people can please give us feedback on our first hybrid event, as well as the topic that we've discussed on the use of QR code on the slide. With everything else, the PFD of the slides will be sent out by Murat and YouTube, and the presentation recording will be uploaded to YouTube in due course. Probably look for it in about a month's time. I think it should be up there. I think so. That's what we discussed. Without any further ado, I will draw the meeting to a close and thank you very much for your attendance.
Thank you.
Thank you.
Thank you.
Thank you very much.